Welcome to this episode of the Kubernetes Cloud Series. Today, we're exploring EKS Fargate, Amazon's serverless solution for running Kubernetes pods. With EKS Fargate, you can run your containerized applications on AWS without the burden of managing the underlying server infrastructure. This means no more worrying about provisioning nodes, configuring instance types, or maintaining server fleets. Let's dive into how Fargate transforms the way we deploy Kubernetes workloads on Amazon Web Services. EKS Fargate is Amazon's serverless compute engine designed specifically for containers. It provides on-demand, right-sized compute capacity without requiring you to provision or manage EC2 instances. Think of it as a fully automated infrastructure layer. When you deploy a pod, Fargate automatically allocates the exact amount of CPU and memory needed. The key benefit is eliminating node management entirely. You don't need to worry about node groups, scaling configurations, operating system patches, or any infrastructure maintenance tasks. You simply deploy your pods, and Fargate handles everything else behind the scenes. Let's compare traditional EKS with EKS Fargate to understand the differences. With EC2 node groups, you're responsible for managing EC2 instances, configuring node scaling policies, handling operating system patching, and paying for nodes whether they're fully utilized or not. In contrast, Fargate eliminates all of this operational overhead. There's no instance management whatsoever. Scaling happens automatically as you deploy or remove pods. AWS manages the entire infrastructure stack for you. And most importantly, you only pay for the actual resources consumed by your running pods, not for idle capacity. This fundamentally shifts you from managing infrastructure to focusing purely on your applications. Understanding the architecture of EKS Fargate requires knowing three key components. First, the Fargate profile defines which pods should run on Fargate infrastructure. It uses namespace and label selectors to match specific pods. Second, the pod execution role is an IAM role that grants permissions to the Fargate infrastructure. This role allows Fargate to perform critical tasks like pulling container images from Amazon ECR and writing logs to CloudWatch. Third, the Virtual Kubelet. Behind the scenes, AWS manages virtual nodes that represent Fargate capacity in your cluster. These virtual nodes integrate seamlessly with Kubernetes, appearing as regular nodes in your cluster, but they're fully managed by Amazon. Creating a Fargate profile is straightforward using a YAML configuration. The profile defines which pods will be scheduled on Fargate infrastructure. In this example, we're creating a profile named my -Fargate profile. The selectors section is crucial. Here, we specify that any pod in the production namespace with the label compute equals Fargate will run on Fargate. You can add up to 5 selectors in a single profile, allowing fine-grained control over which workloads use serverless compute. If a pod matches multiple profiles, you can specify which profile to use by adding a specific Kubernetes label to the pod specification. EKS Fargate offers 4 major benefits for Kubernetes deployments. First, simplified operations. You eliminate server management, patching, and capacity planning entirely, allowing your team to focus on application development. Second, enhanced isolation. Each pod runs in its own dedicated compute environment, providing better security boundaries between workloads. Third, pay-per-pod pricing. You only pay for the vCPU and memory resources that your running pods actually consume, eliminating costs from idle infrastructure. Fourth, automatic scaling. The infrastructure scales automatically as you deploy more pods. There's no need to pre-provision capacity or configure complex auto-scaling rules. Fargate adjusts compute resources dynamically based on your actual workload demands. While Fargate offers many advantages, it's important to understand its limitations. First, daemon sets are not supported on Fargate nodes. If your application relies on daemon sets for node-level services, you'll need to use EC2 nodes instead. Second, ephemeral storage is limited to 20 gigabytes per pod. If your workloads require more temporary storage, this constraint might be problematic. Third, privileged containers and host network mode are not supported due to security isolation requirements. Finally, cold start latency is a consideration. Pods take approximately 30 to 60 seconds longer to start on Fargate compared to EC2 nodes, because Fargate must provision the underlying infrastructure for each pod. For latency-sensitive applications, this startup time should be factored into your architecture. Fargate excels in specific use cases. Batch jobs and CI/CD pipelines are ideal candidates because they need instant scaling without maintaining idle infrastructure between runs. Microservices architectures benefit from Fargate's ability to isolate each service in its own compute environment with automatic resource allocation. This eliminates the complexity of bin packing multiple services onto shared nodes. Development and testing environments are perfect for Fargate because teams can rapidly deploy test environments without managing underlying infrastructure. The pay-per-pod model also makes testing more cost-effective. Generally, Fargate works best for workloads with variable traffic patterns, applications that don't require privileged access, and teams that want to minimize operational overhead while maximizing development velocity.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.